Yeah. So the directrix is your line, and you have your focus, and the points on a parabola are going to be an equal distance from the focus to wherever the parabola is at, and then from that point down to where the directrix is at. All right? Now, the key point has to be exactly halfway between them, right here. That's called the vertex. Okay, that's the vertex. It has to be exactly halfway between them. Is that cool? Because it's got to be an equal distance from both of them, so it's got to be right in the middle. Now, if you look here, there's a point that's going to be the same distance here down to here, right? And what? Here to here. Does that look like I'm holding my finger in about the right place? It'd be equal from here to here, and what? From here down to here. Is that good? Look at that point. Now, if you think about it, there's another one over here that lines up with that, where this is a horizontal. Is that about right? Is that pretty good to where the distance from where I just put the point to here, and the distance down to here is the what? Same. Is that okay? Now, if I put a point up here, it gets a little harder when you get up here. If I put a point, does that look about right? Does that look pretty close to right? Okay. And what happens is you get your parabola shape. And I guess what I'm trying to get at is not all U-shapes are parabolas. They have this special idea. I'm going to put an XY here. X comma Y. So, distance from the focus to parabola point on parabola. Put the point. We know we're talking about parabolas. Just put distance, focus to point equals directrix, distance directrix to point. To point. All right? Pretty cool? Okay. Now, a lot of times we'll draw this. We'll draw a little line here, draw a little curve. We'll put our little focus, and we'll say this distance has to equal what? That distance. Okay? That's a little drawing to explain it. Directrix, hyperbola, parabola. All right? Of course, you got a vertex there. Just put it in here. All right. But that's the key to drawing correct parabolas. Not just something that's made up to be close to a parabola. Okay. Now, back to our drawing over here. I meant for these points, all three, to be on a horizontal line there. And I'm going to make sure everybody's happy before I start writing anything else on this graph. Because this is the key here. This is what you've got to have. All right. Just so we're all calling it the same thing, we're going to call P the distance from the vertex to the focus. Which means it's also P from the vertex to the what? Directrix. Now, why did we pick P? I don't know. I don't know why we picked P, but that's what we're going to use. We're not going to use anything else. We're going to use that P distance. We're going to know that that distance is P. And if that's P to here, and that's P to here, would everybody agree it's 2P from the focus down to here? Is everyone okay that that's 2P from here to here? That means it's 2P from here to here, right? Which means it's also what? 2P from that key point and 2P over here. Now, those 2 points that are out here on the side, they come in real handy because they tell you how big the opening is. Those points are called the latus recti. And I don't have to talk about that because we've already learned about it. Latus recti. Latus recti. Okay. And that gives you the key information for a parabola. Now, some parabolas open up. Some parabolas open down. If I could turn this upside down, you would have a parabola that did what? Opened down. All the p-values and all that stuff would still be the same. It's just that now it would be pointed down. Oh, what happens if it's pointing to the left? Or what happens if it points to the right? And I don't know which way it's really pointing now. But do you notice, for those people at home, I'm just having a little fun there, and for you in class, just so you'll pay attention and listen, and not, because it always helps if you're doing something kind of fun to make you listen. But the deal is, this is key because no matter which direction the parabola points, this is our key information. We can turn the page any way we need to work with parabolas. All right, we're going to get back to the picture in just a moment, but we're going to talk about the fun thing about parabolas. I'm drawing this over here because I don't want to mess up my picture. All right, if you have a true parabola, true parabolas, shapes, and I'll try to draw a true parabola here. You got your vertex, and you got your focus. Looks about right. Focus. Here's what's really cool about real parabolas. In the real parabolas, if you have an energy, a light wave come in, or a sound wave, or any kind of energy wave, they will come in, they will hit the parabola, and they will bounce to the focus. All right? A little bit like an ellipse, except it doesn't work backwards like an ellipse. Ellipse, you can send it from either focus to the other one. But parabolas, really nice, because as this comes in, bounces, it will bounce to the focus. Now, imagine if this were three-dimensional. Look kind of like a bowl, wouldn't it? Yeah, 3D bowl. Parabolic bowl. How do you spell a bowl? B-O-W-L? Okay. Bowl. Parabolic bowl. Okay? Now, so if you're, if you want to get it real hot, set it out in the sun, have it made of mirrors, parabolic bowl made of mirrors, and hold your finger right at the focus. It's going to get real hot right there because it's doing what? All that energy is being focused to that one point. You see examples of parabolic bowls every day. I mean, almost every day. It's pretty hard not to see them anymore. Anyone? Where do you see examples of parabolic bowls all the time? I am not going to move on until you at least try to answer the question.
Well, like headlights, is that?
Okay, headlights.
Sort of the opposite.
Yeah, the light comes off the light and then they focus it down the road. Don't know. Maybe. I'm going to guess there's something to do with conic sections in there. I would try that. I'd put that down as an answer, at least hope for some partial credit, because I think it's a pretty good thought. I had one more specific in mind. A bowl shape. It's got a little receiver that is out here inside the bowl. It'll have a little arm and it holds this little receiver out here in the bowl.
So, yeah. It's like a dish.
satellite dishes. Dish TV, folks. The dish. Satellite. I don't know how to spell satellite, so I don't want to put that up there. Yeah, but it's dish. Satellite dish. There's two in the yard right over there. See, there's two over there. There's a couple on our building. But here's the catch. You ever notice you have a storm and something falls and it hits in your satellite dish and it moves that arm, it bends that arm, right? So what you do is you take your 12-year-old son and you go, hey, I need you to go up there on the roof and I want you to move that around and I'll yell at you when the picture gets better. Because what's happened, that receiver needs to be at the focus. And when that tree hit it and moved it, it's no longer at the what? Focus. Now, I know you're sending your 12-year-old son up there in the middle of a lightning storm, a thunderstorm with lots of lightning, to do this so that you can watch Dallas lose. But still, you know, that's what you have to do. Now, sometimes people will say, every time it rains a whole lot, or if we get ice or snow, my dish doesn't work very well. Well, imagine what happens when you get something in here that's reflecting the waves and it's no longer smooth down here. What happens? They don't reflect to the what? Yeah, they don't reflect where they need to. But yeah, satellite dish is the perfect example of parabola. So I kind of like that one because it's easy for me to give you an example. Mr. Evans, where do you ever use math in the real world? Well, there you go. I was teaching you hyperbolas the other day. Notice I didn't give you any real world examples of hyperbolas. And notice we didn't spend much time on them. Hyperbolic functions, I don't know a lot about any applications for those. But I think when you break the sound barrier, at the moment you break the sound barrier, instead of the sound waves being sine waves, that you get a hyperbolic curve coming off the nose of that jet. Okay, if you look at the pictures, that's what it looks like to me. They'll show the jet just as it breaks the sound barrier. And if you'll notice, it looks like you're getting hyperbolic curves coming off of it. But parabolas are everywhere, all right? Parabolas are used for a lot of stuff. And they may be used, you know, you put the light here and get everything to reflect down in the other direction. I like that. Put the light to focus, and that would probably put more light going down here instead of light, because I think that would work. I'm pretty certain. I'd look that up and find out for me. All right, now I'm feeling really bad about making fun of you at the beginning of class. Okay. All right. Now, let's actually use this picture to work with the parabola information. We're going to start off with our parabolas. I gotta have a pen that writes starter now. We're going to start off with our parabolas, and y equals a x minus h squared plus k. The first thing is the x is squared. The x is squared. These parabolas either open up or they open down. Okay? The x is squared, but you got your y equals here. If the a value, the value out front, is a positive, these open up. If the a value, get a positive a, they open up. If you have a negative a, they open down. Okay? The vertex for these, vertex, is h comma k. As long as that's a minus sign there and that's a plus sign there. All right? Okay? Then it's h comma k. And y'all know what to do if one of them's positive or negative because you did that with circles. Then, the key to the whole story so that you can use this picture. Notice, I talked a lot about the p-value and I told you that's what you have to use, right? Okay? Notes? I mean, you can watch the video at home if you want to. I mean, that's cool. But I put some notes down. All right. Here's the key. 1 over 4p equals the absolute value of a. The p has to be in the denominator. It's not 1/4 of p. It's 1 over 4 times p, and the p is where? In the denominator. I'm looking, because I got people that put 1/4 p all the time on work. P is where? In the, use a horizontal line so that you know the p and the 4 underneath. And use one of those diagonal lines for your fractions. Just makes it look messy. All right. Now, with that information and with this drawing, graphing a parabola is pretty easy. Are we ready? Notice there's not a lot of information there. Okay. And I didn't give you a bunch of formulas because I'm going to help, hopefully you're going to rely on that visual. See, I don't have to give you a lot of formulas as long as you P, 2P, 2P. You know, I don't have to put a bunch of formulas up here because I'm hoping you rely on that visual. All right, let's work the problem. Out here, no, don't erase yet. Okay, here we go. Now, somebody that's watching these is going to say, well, you're not a very good teacher. You never let your students ask questions. That's right. Y equals 1/12 x plus 1 squared plus 3. Changes the 3 to a 2. All right, here we go. I'm going to draw, erase my drawing. The first thing you really need to do is make sure you find the vertex. And you also need to know which direction it opens. Find the vertex, decide which direction it opens. Oh, nice big pretty drawing. Make your graphs big. Okay, the vertex is -1, 2. Everyone okay that has to be a negative sign there, so that makes a negative, negative. But if you look at the rule and you got it written down, that's already supposed to be a what? A positive. So -1 and then up 2. Vertex. Now, once you have the vertex and you know it opens up, you need the p-value because that tells you how to count. So you go 1 over 4p equals 12. I did tell y'all it's absolute value of a, didn't I? Did I remember? Yeah, I did say what's that. Okay. 1. Oh, I'll put all that on video. I won't be in trouble now. P equals 3. Is everyone okay at p equals 3? Do you realize if you put 1/4 p, you don't get the same thing, do you? Someone says, Mr. Evans, did we cross multiply? Please don't say that out loud. You multiply by the common denominator is what you say out loud. Yes, you cross multiply, but that's not a math term. It's multiplied by the common denominator. I don't want you laughed out of your classroom in college. Okay, we count up 3, -1, 5. There's our focus. And we count down 3, and here's where you got to be a little bit careful. Your directrix is a line, it's not a point. It's y equals -1. All right? Because 2 minus 3 is how much? -1. And you were changing the y value, it's y equals -1. And there's your directrix. I went up 3, and I went what? Down 3. So far, so good? Now, when I get to looking for the latus recti, I multiply that by 2. 2p. I'm not even going to put that down here. 2p equals 6. So, we're going to go 6 to the right. Negative 1 plus 6 is 5. Negative 1 minus 6 is negative 7. And those are our lattice recti. I'm just going to put LR. I don't mind if you just put. And now when you draw your parabola, you can make a nice graph of it without, you get a pretty good graph. It makes your graph pretty active. There you go. And those are called the lattice recti. I didn't tell you about one bit. I'll make sure everyone's okay up to here. Take a moment. Look at the children's faces, see if they look happy about life. See if one of them looks frustrated because they didn't get the right numbers. So far, so good? Okay, there's something that a lot of people put on these graphs that I just can't do. I cannot mess up my graph. Does everybody see that straight through here there's an axis of symmetry? I will write axis of symmetry, and I will put x equals negative 1. But I will not put a dotted line right through the middle of my parabola. I just can't do it. It's just wrong. It's not aesthetically pleasing. Okay. I didn't ask you to find x-intercepts and y-intercepts. In the past I have, but I'm not going to this year because we're going to get back to that along the way. I just need a good parabola shape. All right. I think this is, his last name is Livio. And the only reason I'm saying I think that is because, I'll tell you who he is. He was the theoretical physicist for NASA. And I think his name was Livio. Theoretical physicist for NASA. And one of the things that he talks about, if you read his books, writes about, or if you hear him speak or whatever, is he talks about where you see symmetry in nature. He's real big on looking for where you have symmetry in nature or in the universe. You know, like where do you have symmetry in animals? Where do you have symmetry in buildings? Where do you have symmetry in the universe? And why do you see these symmetries? Now, if you think about symmetry about a line, that's pretty easy. Unsymmetric left to right. Is everybody okay with that? Unsymmetric left to right. I'm not symmetric top to bottom. Unsymmetric what? Left to right. Now, if you think about a starfish, they're really symmetric more about a point. Is that okay? You know, think about your starfish, and Mr. Evans can't draw a starfish. I mean, you know, let's be real, but if you look at your starfish, your little starfish, he's symmetric around a point. You might think a flower is symmetric around a point. Is that okay? Now, your starfish, you could also slice him this way, and he would be symmetric what? Top to bottom. If you think about ocean, my goldfish, gosh, we could brought some goldfish and eat them for this class. But if you think about my goldfish, he's symmetric, definitely more what? Top to bottom. Yeah, I know on the bottom, he's got two different fins on the bottom, and up top he's got the one fin up top, right? But he's still pretty much symmetric what? Top to bottom. Now, if you looked at him head on, he would also be pretty symmetric what? Left to right. Now, he's not symmetric from head to tail, is he? See? Yeah, he wouldn't. Yeah, he's not symmetric head to tail. Now, my human, it's pretty easy just to divide my human straight down the middle. All right, he's symmetric, just slicing right down the middle. So symmetry is important, and understanding maybe why symmetries are different for those creatures. Why is the symmetry different for my fish, my starfish, and my human?
Different shapes.
Yeah, they're different shapes, they have different symmetry, but why do they have different shapes? Why is the human symmetric left to right, and these fish are symmetric top to bottom? Look at your dog. He's not symmetric top to bottom, is he? But he's symmetric what? Left to right. He's got those four legs down there running through the house and tapping his paws on the floor. That's what makes it a home. Come on. You got to take part. You got to think. Give me some kind of information. Why would my dog and me be symmetric left to right but not top to bottom? And fish, starfish, waiting. Tell me something that's different about them.
One has legs, one doesn't.
Yeah, and why is that?
Because,
Keep going. You're giving it a shot.
because humans and dogs, they use their legs to get around. But when you're underwater, you're going to use your hands to move.
What's the difference between the situation if you're underwater or if you're in the water versus being on the land?
You don't use your legs as much.
Oh, okay. Now, if I'm in the water, okay, what we've decided is he needs to be able to move through water to get away from everything and not be eaten, right? And I need to be able to get around on the land so that I don't get eaten, right? What makes those two environments different? You're on the right track. You're thinking. Someone else want to help him out here. Take another step with it, or I give him all the points, give everybody else a 0. Someone. Be willing to be wrong even. Someone. Try something. Say anything. What makes their environments different?
Humans are up and down, fish are flat.
And why? Do any of y'all swim? Any of y'all play in the pool?
Who's faster
Fast, yeah, he's going to be faster that way than he is, so he's going to get away from the bigger fish and make it, right? Okay. Does anyone teach swim lessons? Did anyone take swim lessons? All right. When you were taking swim lessons, did the person hold you up in the water and let you learn to swim? Kind of put their hand on your belly and hold you there while you learn to swim? Is that kind of how they teach swim lessons now?
I don't know, I was too young.
Too young.
I don't know.
Okay. Does anybody play in the water and notice something about when you're in the water versus being out here on land?
And there's gravity feels different.
Yeah, when you're in the water, you're not overcoming gravity because you can float, right? You're not having to overcome gravity. You're having to overcome the water resistance. Your propulsion's here making you go that way. Hey, to go up and down is not a big deal, is it? But for a human to get around, and for dogs to get around, and for all these animals that are out here on land to get around, we've got to make sure that, what? We've got legs that are powerful to move us. See, the symmetry for us is left to right, because we can't be symmetric top to bottom, because if we were symmetric top to bottom, and I was trying to run away from the big animals back there a couple thousand million years ago, I wouldn't have enough strength to run away, would I? So see, how we get around, we're having to overcome gravity. These guys are not having to overcome gravity. So when you look at symmetry,